Hello everybody and welcome back to the channel. If you like my content, please like and subscribe. This week we're going to be looking at oxygen uptake kinetics. This is, if you like, my first love in research, and I thought I'd look into this for the simple reason that it's sometimes very difficult to get your head around. In fact, I go so far as to say that anybody who I meet at a conference looks at me in exactly the same way that Obama is looking at me right now. So, what is oxygen uptake kinetics? It's a very good question. Fundamentally, what it is the pattern of the oxygen uptake response to a set exercise challenge. Now, usually, but not always, that challenge is a sudden increase in work rate, power output, running speed, or something similar. That then produces a characteristic response, and measuring that response is essentially measuring the oxygen uptake kinetics. Today we're going to focus exclusively on moderate intensity exercise, and that's its own jargon. That simply means exercise performed below the lactate threshold. And we're going to focus on the notion of a mono-exponential decay. What that actually means in the case of VO2 kinetics is when you start exercise, the mono-exponential decay actually goes upwards, which is what you're seeing here in the slide. So VO2 kinetics rises, or the VO2 response I should say, rises and reaches a steady state. We'll discuss this in a bit more detail in a moment. But if you stop exercise, it will then decay back downwards in a mirror image fashion. Then we have the parameters of the oxygen uptake response, and this is where people often get confused. So when we talk about the oxygen uptake kinetics and how fast the oxygen uptake kinetics is, we're really talking about the value of the time constant. And the time constant of the response tells us how fast this curve goes up to the steady state. And the time constant is given the Greek symbol tau, or as the Greeks actually pronounce it, taf. But I'll keep calling it tau because everybody else does. And what this does is give us a measure of the rapidity with which the oxygen uptake responds. And the time constant is the time taken to reach 63% of the final amplitude. And the amplitude itself is how high the oxygen uptake rises as a consequence of the exercise challenge. That's what we call the amplitude. And then there's also sometimes a time delay, because when you're measuring oxygen uptake kinetics, you want to know what's happening at the muscle, and you're taking measurements at the mouth, as I'll describe in a moment. And so sometimes you have to put in a time delay, in fact all the time you have to put in a time delay in order to account for the time it takes the blood to get from the muscle to the lung. And we also talk about mean response time and effective time constant, and that's the time delay plus the time constant. And the reason that's useful is not only is it another measure of the speed of the oxygen uptake response, but if you multiply this value, the time delay plus the time constant measured in minutes, by the amplitude, that gives you a measure of the oxygen deficit without having to do any integration or anything like that. A simple calculation will give you an approximate value for the oxygen deficit, which is obviously this area here. How do we go about measuring all of this stuff? Well, for those of you that don't know, pulmonary oxygen uptake is essentially the use of the measurements of expired air to calculate the amount of oxygen that's actually extracted from that air and transported around the body and ultimately used. So this is pulmonary oxygen uptake. Broadly speaking, there are two ways of doing it. So here we have the Douglas bag method, and what's happening is there's a three-way breathing valve here, so inspired air comes in here, expired air goes through that tube exclusively, and when you turn the tap, the air ends up in that bag. What you then need to do is sample the gas concentrations in the expired air that you've collected in the bag, and also measure the gas volume, and record the time over which you recorded the measurement, and then you can calculate the rate of oxygen uptake, taking into account the prevailing temperature and pressure, which you can see written on the board behind the experimenter and the participant. So that's the Douglas bag measure method, and usually you can get about 30 to 60 seconds of exercise is required, 30 to 60 seconds of expired air sample is required to get meaningful measurements of VO2 using that system. It's very, very useful because it's a system or a measurement based on first principles. So it's very, very easy to log and track your errors and correct them if you need to. The other way of doing it is with breath by breath analysis, and that's what you're seeing here. Essentially what you do is turn each breath into a Douglas bag. And so we have a turbine in here, and we also have a sample tube which is taking expired gas or sampling the gas continuously, I should say, and you can just about see the ports for the analyzer on the side there. You also have a spit tube here because with the nose clip and mouthpiece you cannot swallow, and so you have to collect the saliva because you don't want the saliva interfering with the turbine. If it does, you're in big trouble because you won't record any breaths. But when we're doing measures of the oxygen uptake kinetics, we usually have to rely on breath by breath measurement because that will give us the maximum number of data points that we can then characterize the curves with. But when this was first done back in the day, A.V. Hill didn't have that luxury. He wasn't the first to characterize the oxygen uptake response. Fletcher and Hopkins before him and Kroll and Lindhard also did it, but he was the first really to grapple with and grasp the concept of what was really going on. And so what you see here is these are data from A.V. Hill actually running himself. And so here you see the resting value about 0.3, 0.4 litres per minute, and then he immediately starts running, and if memory serves me correctly, he's running at about approximately 12 kilometers per hour, and then he's measuring expired air at various time points. Now he would have had to have done this repeatedly to get these measurements, so he would have run for the 30 seconds at that speed, stopped and then recorded it, and so on and so forth. So it would have taken him all day to collect these data. But what he showed was that there's a lag in oxygen uptake, and it takes about 2 to 3 minutes before oxygen uptake reaches a steady state, as we call it. And he correctly identified that in that steady state, the energy demand of the task is met by aerobic energy supply. But he also recognized that the energy demand of the task was set right from the very beginning. And so there was a deficit phase in which the energy had to be coming from somewhere else. And he called this the oxygen deficit. And at the offset of exercise, he called the difference between the VO2 and the actual requirement the oxygen debt. So he's using financial terms. But it's very important to note that when we talk about the oxygen deficit, we are not suggesting that oxygen is deficient. It isn't. What it is an energy deficit. So there must be an energetic equivalent in this region which is derived from non-oxidative sources, not derived from the consumption of oxygen. And A.V. Hill said that's probably lactic acid, and that accounts for that deficit. So anaerobic glycolysis, we might call it. And we can laugh at A.V. Hill for that because we know it's wrong now. But his suggestion predates the discovery of ATP and phosphocreatine by several years. So this is a very important point. What Hill did was get the concept right, but the details wrong. And I would argue in any branch of science, getting the concept right is more important than the details, because you can fill in the details at a later date. This is the right concept, and indeed the oxygen uptake response you see here and the characterization of it was not improved for at least 50 years until the late 1960s, early 1970s with Wasserman and Whip and other researchers investigating breath by breath records. On the subject of Whip's data, these are some of the data collected by Harry Rossiter in the late 1990s. I'll come on to why a little bit later on. But what you see here is a higher sampling frequency. This time the data are averaged every 10 seconds. So there's breath by breath data, and then the data have been subsequently averaged. But what Whip in the early 1980s showed was that there was a 3-phase response to moderate intensity exercise. After the onset of exercise, so you have a baseline here of unloaded pedaling, and this is all on a cycloergometer, and then you have a phase 1 increase in VO2, and we think this is coming from the sudden increase in cardiac output and the sudden increase in pulmonary blood flow, which occurs at the onset of exercise. In other words, this is not blood that's drained the muscle, the exercising muscle, at the onset of exercise. It's the blood that comes before that that enters the pulmonary circulation, and because it suddenly enters it more rapidly, you get an increase in VO2. There's a delay until a further increase in VO2, which does represent, we think, what's going on in the muscle, and then it reaches a steady state after 2 to 3 minutes. So what we have here is the phase 1 or cardiodynamic response, phase 2 or the primary response, and then phase 3, the steady state. Now you might wonder why I was so keen to assert that this phase 2 or primary response reflected what was going on inside the muscle. Well, we know that from work that Bruno Grassi did in the mid-1990s. And what he was working in Peter Wagner's lab, and what he showed was by taking simultaneous measurements of the mouth VO2, in other words, what he's called the alveolar VO2 here, which is essentially just a correction factor you apply to breath-by-breath data. But what he did was measure pulmonary VO2 and simultaneously measure leg VO2 using constant infusion thermodilution. So you essentially inject cold saline, and then downstream you measure the temperature change, and that's related to the rate of blood flow through the vessel, and then you can calculate oxygen uptake by also measuring venous oxygen content. And what you can see here is the kinetics of pulmonary oxygen uptake are within confidence the same as the muscle oxygen uptake kinetics, so the leg VO2, which shows that the oxygen uptake kinetics you measure at the mouth, at least in moderate intensity exercise, faithfully represents what's going on inside the muscle. That's why we're so interested in this primary response. So how do we go about calculating the VO2 kinetics? It's a very good question. I'm glad you asked. Well, what we've got here is a plot of second by second oxygen uptake data. These are the sorts of data we usually use to characterize the response. The reason we interpolate the data from breath by breath to second by second is then we can take a series of similar transitions, similar moderate intensity exercise bouts, and average them together, assuming that the responses are the same each time. That's been shown to be the case. You then reduce the breath to breath noise by doing this. And so that's what we've done here. I think this is, if memory serves me correctly, we've done 3 separate transitions. You can still see there's a lot of noise in the data, and that's characteristic of oxygen uptake data using this technique. It's not something you can ever completely get rid of. So we take that second by second data, and then we start to fit curves to it. The first curve we fit to it is the baseline. We don't really fit a curve to it. What we do is simply take the average of the last 60 seconds of baseline data. This is unloaded cycle pedaling, and then we simply fit a line through that. And the way we fit a line through that is just by putting the numbers into Excel, frankly. Then what we need to do is perform nonlinear regression. So what we do is we select what we think are going to be the parameters. So we take the time constant, the amplitude, and the time delay, and we tell whatever software package we're using, there are a number that you can use, we tell that software package what the initial values are likely to be. So we might say the amplitude is going to be 2 liters per minute, the time constant is going to be 30 seconds, and the time delay is going to be about 15 to 20 seconds, something like that. We put that in there, and then it goes through an iterative fitting routine to try and get the best fit from those initial parameters. And it will then change those parameters until it minimizes the sum of squares. And then it will do something like this. And so you get a reasonably nice fit to the data. That's your curve fit. So what's really going on here? Let's put some flesh on the bones. So what I've done here is I've simply added the oxygen deficit. So this is the square wave increase in exercise demand. And then I've also put a dotted line down here so you can look at the amplitude. So the way we fit these data is with the following equation, which says that VO2 at any time after exercise onset is equal to the baseline VO2 plus the primary amplitude, which is the distance between this dotted line and this solid line in the steady state, multiplied by a mono-exponential function. And this mono-exponential function includes the time delay, which you see here, and the time constant. Now you can't see the time constant, but that characterizes how rapidly the curve rises. Now, the key thing here is that we're basing all of this on the natural number e. And because e is equal to 2.71828, you might then wonder why it is the time constant is specifically 63% of the final amplitude. Well, we can answer that because when the time is equal to the time constant, and let's just ignore the time delay for now, then that whole equation there reduces to e to the minus 1, which is 0.37. And so therefore 1 minus e to the minus 1 is 0.63, which means that everything in these parentheses simply collapses to 0.63. So when time is equal to the time constant, we are multiplying the amplitude by 0.63, so we've reached 63% of the final amplitude, and that is what the time constant is all about. So if you think about it, that's actually quite straightforward. It's not that much more difficult than fitting a straight line to normal data. It's just that you have to select initial values and do it with non-linear regression. But this curve's quite interesting. So we can look at what happens if we play about with the equation. And if you haven't followed that last slide, don't worry, because we're going to do it in words as well. So that's the original equation that you've just seen. And what this equation really says is when you fit the data, please decay upwards exponentially from the baseline by the value of the amplitude. That's what that equation tells the curve to do. You can change some of these things. So let's say we change the equation to this. So we get rid of the minus 1. So what happens there? Well, what you're then saying is start at the primary amplitude, that value, and then decay exponentially downwards. And so that's what that equation would look like if you tried to fit it. Now if you start with the baseline VO2 being equal to the primary amplitude, then you'd essentially be characterizing the kinetics of the off transient or the recovery phase. So if you want to look at recovery oxygen uptake kinetics, you would essentially use this equation, but the baseline VO2 would be your on kinetics primary amplitude. You can also do this in a different way, so you can take the plus sign, so all we're doing really here is changing the signs. You do that, and that then says decay exponentially from the baseline by an amount represented by the amplitude. And then you get something like this. Now, this looks exactly like the offset of exercise, but of course, unfortunately, we've screwed things up a bit. We started from the baseline and then we've gone downwards, so we end up with a negative amplitude or a negative primary amplitude. This would imply that you are photosynthesizing, and as Kermit has always said, it's not easy being green. So that's just playing about with the equation a little bit, and that's all this equation does, is fit a mono-exponential function to whatever you ask it to in a way you ask it to do it. The most important thing I want to tell you before the end of this is that the primary component reflects muscle bioenergetics. And so the moderate intensity VO2 kinetics is a window into muscle metabolic control, and for my money the best demonstration of this was produced by Harry Rossiter, as I've already mentioned, because this is the previous VO2 response you saw a few slides ago, but what he did here and what his group did was simultaneously measure pulmonary oxygen uptake and phosphocreatine degradation in the muscle. They did this by lying prone in a magnet and kicking both legs, and they were measuring oxygen uptake at the mouth, and they had a coil on the muscle, and they're measuring muscle phosphocreatine simultaneously. Now the key thing here is that we have creatine kinase in the muscle. That's there to break down phosphocreatine to resynthesize ATP and keep cellular work going. That happens in the cytoplasm. But we also know there's creatine kinase found in the mitochondria, and that's used to resynthesize phosphocreatine from the mitochondrially produced or the aerobically produced ATP. And so creatine and inorganic phosphate will enter the mitochondria. ATP synthase will manufacture the ATP, and that ATP will then be used to resynthesize phosphocreatine, which is then shuttled off to another part of the cell. And so in that way, phosphocreatine acts as both a spatial and temporal energy buffer. It stops energy having to fly here, there, and everywhere. It stops the mitochondria having to be everywhere at the same time, but it also slows things down. It means the mitochondria don't have to immediately increase oxygen uptake at the onset of exercise, because what Rossiter and colleagues showed was that this increase in oxygen uptake and the kinetics of that increase were identical to the kinetics of phosphocreatine degradation. So what's happening here is as phosphocreatine starts to decline, that immediately signals to the mitochondria to start increasing oxygen uptake, which they do, or oxygen consumption, which they do, which slows the rate of decline of phosphocreatine, which slows the oxygen uptake, and so on and so forth, until both variables reach a steady state. And that's why VO2 kinetics measured at the mouth is so important, because it gives us that window into metabolic control. And so thank you very much for listening to this introductory session. I'm very glad that Obama is now pleased with my explanation. Next time we're going to look in part 2 at the slow component and higher intensity exercise. Thank you very, very much for your attention. Please do like and subscribe if you found this interesting. I'll catch you later.